Welcome back for this next lecture on refrigeration and air conditioning. Till today we have discussed the various points regarding with the refrigeration. So in the first part we have discussed introduction of refrigeration unit and coefficient of performance. After that we have discussed the comparison between heat pump, heat engine and refrigerator. Then one of the most important cycle in a refrigeration, the reverse Carnot cycle, and the formula for the reverse Carnot cycle that we have discussed. Now, then we have discussed the Bell Coleman cycle and the formula for the Bell Coleman cycle. Now next, the simple part, that is a closed loop Bell Coleman cycle. The previous which we have discussed, it's an open loop Bell Coleman cycle. So this is a closed loop Bell Coleman cycle. So just I have drawn here one expander, and along with the expander the remaining refrigeration system is as it is: compressor, condenser and a refrigerator. So from this expander, when the cold air is got into the refrigeration chamber, so what happens in the refrigeration chambers, the coils are provided, and these coils are carrying the cold air, and this refrigerator space that's surrounded by the brine solution. Now what is a brine? Brine is a mixture of sodium chloride or salt with water. So why the brine is used? Because the water freezing point is 0 degree Celsius. So in some cases where the requirement is below 0 degree Celsius, so at that time you cannot use a water. So for using the water below 0 degree Celsius, we are adding the salt, and that salt will decrease the boiling point of freezing point of water. So here the cold chamber is provided, and this cold chamber is consisting of a brine solution. This brine solution is acts as a cooling medium. So what happens? This brine solution, it absorbs the heat from the expander or gets cooling effect, and this cold brine is goes to the cold chamber. When it goes to the cold chamber, it rejects heat to the cold chamber and it absorbs heat the cold chamber, and then it returns back to the refrigerated space. So this is the closed loop system in which the refrigerator as well as the indirect brine solution comes into the picture. There will not be the open loop system. So here this hot brine, when comes into the refrigerator, what happens? It becomes cold. Then this cold brine is transfers to the cold chamber, and the cold chamber gives its coldness, and it absorbs the heat from the cold chamber, and this hot brine solution is again pumped with the help of brine pump into the refrigerator space. So this process, brine solution circuit, is a complete circuit, and again whatever the hot air from the refrigerator space, it again goes to the compressor, and then it goes to the condenser and expander. So in this way, this closed loop Bell Coleman cycle can be operated. Now what is a brine solution? Brine solution is a mixture of salt and water, or you can say that in sodium chloride and water. So if you add the 23% of sodium chloride in the solution, so its freezing point is 21 degrees Celsius. So such a way the brine solutions can be prepared from sodium chloride, calcium chloride, means CaCl2. So when these salts are added into the water, the freezing point of water is fall down. So when the calcium chloride is added inside the water in a definite proportion, so at that time the freezing point of water is falls below the minus 55 degrees Celsius. So these are the advantages of the brine solution, so that the easily available water which can be used as a refrigerant by using the salts, and this is possible in case of below 0 degrees Celsius. So hope you have understood this point. The Bell Coleman cycle, we will just take a quick review. The COP of Bell Coleman cycle, the formula is Equation number 1, the formula is for COP of a Bell Coleman cycle. If the 4 temperatures are given, T1 minus T4 divided by T2 minus T3 minus T1 minus T4. This is the formula for the Bell Coleman cycle. If the pressure ratio is given, then equation number 6, COP is 1 upon pressure ratio Rp raised to gamma minus 1 upon gamma minus 1. Here Rp is the pressure ratio, P2 by P1 or P3 by P4. Gamma is adiabatic index, which is always equal to 1.4. So hope you have understood this point. Then we will discuss the numericals. Now the first numerical, please read this numerical. An air refrigeration system operating on a Bell Coleman cycle draws air from a cold chamber at a pressure of 1 bar and temperature of 10 degrees Celsius. It is then compressed in the compressor up to a pressure of 5 bar, and after being cooled at constant pressure up to a temperature of 40 degrees Celsius, it enters in the expander. It enters in the expander, assuming both the compression and expansion processes to be isentropic. Calculate the COP of the system. Take Cp of air is equal to 1.005 kilojoule per kg Kelvin, or somewhere it can be given as 1005 joule per kg Kelvin. And gamma value for isentropic process is always equal to 1.4. So please read this carefully. What they have given one refrigeration system is there, and that refrigeration system is operating on a Bell Coleman cycle. So when it operates on a Bell Coleman cycle, what happens? It draws the air. It draws air from a cold chamber, and that cold chamber pressure is 1 bar, and the temperature is 10 degrees Celsius. Now first we will draw the PV diagram as shown in this figure. 1 to 2 isentropic compression process, 2 to 3 constant pressure heat rejection process, 3 to 4 isentropic expansion process, and 4 to 1 constant pressure heat addition process. So here the lower pressure limit is given. It draws the air from cold chamber. Cold chamber pressure is P1 is equal to P4 is equal to 1 bar, and the temperature, that is a T1, is equal to it draws air from, so T4 is equal to it draws air from expander, so it draws air from cold chamber. So after the cold chamber the point is 1, so T1 is equal to 10 degrees Celsius. Now next, it is then compressed in the compressor. So 1 to 2 action takes place. What happens? The compression action takes place. Up to where? Up to the 5 bar. Initial pressure is 1 bar. After compression, pressure becomes 5 bar. So 1 to 2 is a compression process, and at point 2 the pressure is P2 is equal to P3 is equal to 5 bar. And then after being cooled at constant pressure, so from point 2 point 3 the pressure is constant. The point 2 is end of compression. So after compression it is gets cooled at constant pressure, means point 2 process 2 to 3 is carried out at constant pressure. So P2 is equal to P3 is equal to 5 bar. At constant pressure up to a temperature of 40 degrees Celsius, it enters the expander. Now point number 1 is entry of compressor. Point number 2 is entry of condenser. Point number 3 is entry of expander, and point number 4 is entry of cold chamber. So here it enters the expander. Now what is the entry point of expander? Point number 3, and their temperature is given as 40 degrees Celsius. So we will write here the given data. So T1 is equal to 10 degrees Celsius, but Cp is given in case of Kelvin, so we will convert into the Kelvin. So T1 is equal to 10 degrees Celsius, 10 plus 273 degree Kelvin is equal to 283 Kelvin. Initial pressure P1 is equal to P4 is equal to 1 bar. Then the T3, the entry of expander temperature is T3 is equal to 313 degrees Celsius Kelvin, 40 plus 273. Now second pressure P2 is equal to P3 is equal to 5 bar, and Cp and gamma is given. Now the formula for COP, if the process is adiabatic process, so COP is equal to T1 minus T4 divided by T2 minus T3 minus T1 minus T4. So from where this formula comes? So this formula is COP is equal to heat absorbed divided by net work done. So heat absorbed is during 4 to 1 Cp mCp into T1 minus T4, and the heat rejection minus heat absorbed. So heat rejection is mCp T2 minus T3 minus mCp into T1 minus T4. Numerator mCp and denominator we have taken the common as a mCp. So mCp gets cancelled out, and the only remaining is T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Now take the ratio. The process are isentropic process 1 to 2 and process 3 to 4. If you look at the formula of COP, the 4 temperatures are required, and in a given data they have given us T1 and T3. Now we have to calculate the values of T2 and T4. Now first we will take the process 1 to 2. This process 1 to 2 is an isentropic process, and we know the relation between the temperature and pressure. So T2 by T1 is equal to P2 upon P1 raised to gamma minus 1 upon gamma, where gamma is a adiabatic constant, or in case instead of this we can write T2 upon T1 is equal to Rp raised to gamma minus 1 upon gamma. Both the quantities are same because Rp is the pressure ratio. So T2, that value we have to calculate and T1 that we have known it 283. So we will take T2 on one side and other will be transferred to the another side. Sorry, T2 is equal to T1 into P2 upon P1 raised to gamma minus 1 upon gamma. Now what is the value of P2? 5 bar, and P1 is 1 bar, and T1 value is 283, gamma is 1.4. Put all these values, 283 into 5 upon 1 raised to 1.4 minus 1 divided by 0.4, 1.4. So after simplification, the value of T2 is equal to 448.2 Kelvin. Now T1 is given, T3, T4, T1 is given, T3 is given, T2 we have calculated. Now one more term that we have to calculate, that is a T4. So similarly, process 3 to 4 is again a isentropic process. Process 3 to 4 is a isentropic process. So this isentropic expansion process. Now again we know the same relation, T3 upon T4 is equal to P3 upon P4 raised to gamma minus 1 upon gamma. But we will take a reversal of it. T4 upon T3 is equal to P4 upon P3 raised to gamma minus 1 upon gamma. So T4 is equal to 313 raised to into P4 value is equal to P1, and P3 value is equal to P2. So P3 is equal to 5 bar, P4 is equal to 1 bar. So 1 by 5 raised to 1.4 minus 1 divided by 1.4. So therefore after calculation T4 is equal to 197.6. Now we know the all the four temperature values. So therefore COP of a refrigerating system which is working on a Bell Coleman cycle is equal to T1 minus T4 divided by T2 minus T3 upon T1 minus T4. Same formula here we have written. COP is equal to T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Put all these values. Our T1 value is given 283, T4 is calculated 197.6, so 283 minus 197.6 divided by T2 value is calculated 448.2 minus T3 is given 313 Kelvin minus same bracket T1 minus T4. So after calculation and simplification, the value of coefficient of performance COP is equal to 171.5, 1.715, or you can write it as a 1.72. So this is the basic problem on a Bell Coleman cycle. Many times question is asked on this Bell Coleman cycle. In every exam there is one numerical based on this Bell Coleman cycle. So this point is very important. So this is just a basic formula by which we have calculated the coefficient of performance. In the next numericals we will discuss the modified formulas for the coefficient of performance.